So hello guys, welcome back to another video on my channel. In the last video I proved the infinite representation formula for the sine function using a very nice complex analysis trick that I learned from the Basel problem video. In this video I want to actually prove a very nice formula, Stirling's formula, which has many applications in thermodynamics, statistics, statistical mechanics, and of course in probability calculations. So the proof I found online in a research paper. It's a very nice proof. It has very elementary techniques, doesn't require much from us, and I thought, let's give it a go. With that being said, let's get started. So this video is actually going to be structured like a mathematical document, in the sense I'm going to have propositions, lemmas, and then the final theorem. Now, I don't really like this format too much, but it's very effective in conveying ideas, and I think people who are not used to this can start getting used to it, especially if they aspire to go into math academia, because this is the way you have to present your arguments, even though you may understand them in a more intuitive way. Okay, let's get to proposition 1. Proposition 1 says the sequence an equals n factorial divided by square root n to the n e to the minus n, which of course is greater than 0. You can just see that for n greater than 0 converges to a positive number. I know we haven't talked of series and sequences too much, especially sequences, and the theorems that follow for when a sequence converges and when it diverges, because that falls in the domain of real analysis. But here's a nice result that's going to be useful for us. So we need to first show that the sequence an is decreasing, and then that it is bounded from below by a positive number. Because if a sequence decreases and is bound below by a positive number, which follows, makes sense from this, then it converges to a positive number. So we have to do two things to guarantee that it converges. The first step is showing that it's a decreasing sequence and that it's bounded from below. Now there's also the inversion of this, in the sense of if we have an increasing sequence that's bounded from above, then it also converges. Okay, so let's get to the decreasing part. How do we show that it's decreasing? Well, we look at successive terms. So in this case, since we have lots of these powers, n to the n, e to the minus n, where n, which was the indexing variable, is in the power, it's wise to actually consider the quotient rather than the difference. So if we take an divided by an plus 1, we get n factorial divided by square root n to the n e to the minus n, times square root n plus 1, n plus 1 to the n plus 1, e to the minus n minus 1 divided by n plus 1, n factorial. So this term is from the an, and this term is from the 1 over an plus 1. So we can cancel a few things. We get square root n plus 1 divided by square root n plus 1 to the n divided by n to the n times e. Okay, so we can pull the e out, 1 over e, n plus 1 over n, the whole thing raised to 2n plus 1 over 2. So what I've done here is I'm combining the square root, which is power 1/2, with this n, and I'm clubbing that along with the denominator because they have the same power. Now again, the problem here we have is that this is an exponential in n, in the sense the n, which was the indexing variable of the sequence, is in the power as well as in the base. And we know from calculus the best way of dealing with these kinds of things is to consider the natural log, or just any log. Natural log is more standard. So let's define Bn, the sequence Bn, to be the natural log of sequence An. So if we take the natural log on both sides, ln of An divided by An plus 1 equals, we can split this up using the properties of the natural log. We get ln a1, ln An, which is Bn, minus ln An plus 1, which is Bn plus 1, equal to, now the power can drop down and multiply, so 2n plus 1 divided by 2, ln of n plus 1 over n, minus 1 from the 1 over e factor. Okay, fair enough. Now we can actually do a substitution, a change of variables. So set n plus 1 over n equal to 1 plus k divided by 1 minus k. And then if we solve this for k, we get k equals 1 over 2n plus 1 greater than 0. Having done that, we can substitute this back into our little relation there. So 1 over 2k times ln 1 plus k over 1 minus k minus 1. Now we can expand the ln of 1 plus k over 1 minus k. We get ln of 1 plus k minus ln of 1 minus k, and then we can do the Taylor series expansion of this. So k minus k squared over 2 plus k cubed over 3 plus or minus so on, because it's going to alternate signs, minus k squared over 2 minus k cubed over 3 minus dot dot dot. So we can cancel some terms off, not all of them. So we notice we have 2 times just the odd terms. That means k plus k cubed by 3 plus k to the 5 by 5 plus dot dot dot, which we can write nicely in a compact form. 2 times sum from I equals 0 to infinity of k to the 2i plus 1 divided by 2i plus 1. Okay, fair enough. We can substitute all of this back into the bn minus bn plus 1 relation. So we get that sum from I equals 0 to infinity of k to the 2i divided by 2i plus 1 minus 1. And then we notice that for I equals 0, we have the 0 term of this sum is actually k to the 0 over 2 times 0 plus 1 is actually 1. So that we can assume cancels out with the 1 that's up front. So that means we lose the I equals 0 term. That means we can just reindex everything and just start the sum from 1 to infinity by ignoring the I, because that cancelled off with the I equals 0 term. Notice that since k is greater than 0, this entire thing is greater than 0. So what that means in this context is that bn is greater than bn minus 1, which means bn is decreasing because n plus 1 was the next term in the sequence. That's less than the previous term. So that means the sequence bn is decreasing, right? Because n was arbitrary. So now this is the important thing. This is a general observation which I will connect to what we have to this implication we have on top. We know that if f of x is greater than 0 and ln of f of x is decreasing, then f of x is decreasing because if we take the derivative of ln of f of x, we get f prime of x divided by f of x is less than 0, because the ln of f of x is decreasing. That's why the derivative of ln of f of x must be less than 0. And therefore, in this quotient, we know that f of x is positive. That means f prime of x must be negative, because otherwise we won't get a negative number. So similarly, we know that an is greater than 0. That's how we defined it. ln of an equals bn is greater than 0, because the natural log, we know what bn is exactly as well. And bn, the sequence bn is decreasing, which we just got from this implication on top. Therefore, using this observation that we had before for functions, we know that the sequence an must be decreasing too. So in the sense, if if the natural log of an is decreasing, an is decreasing too for an greater than 0. In a way, you can think of this as natural log preserving what the sequence is doing. So if the natural log of a sequence is increasing or decreasing, then the sequence itself inside the argument of the natural log must be increasing or decreasing respectively. So I think that's called the monotone property of the natural log function. Okay, we're done with the decreasing because we just showed that an must be decreasing as well because bn is decreasing. So all that's left is boundedness, right? We need to show it's bounded from below. So first of all, notice that k, which was 1 over 2n plus 1, is of course greater than 0 because n was defined greater than 0, and also is less than 1 because it's all of these guys are just going to be 1 over some odd integer all the time for all the n values. Those are always going to be strictly less than 1 just because they're fractions, like 1 over n, for example. So we have bn minus bn plus 1 equals sum from I equals 1 to infinity k to the 2i over 2i plus 1 is less than, using this inequality, the right side of the inequality, sum from 1 to infinity k square k to the 2i. We can write 2i as 2i minus 2 plus 2, and then we can split them as a product in k. So k squared times the sum from I equals 1 to infinity k to the 2i minus 2 equals k squared sum. Now we can reindex. Instead of starting from 1 because of the minus 2, we can start from 0. I equals 0 to infinity of k to the 2i. Notice that this sum is the sum of an infinite geometric series with common ratio k squared, and it is within its radius of convergence because k is less than 1. So we can use the infinite geometric series formula. We get k squared divided by 1 minus k squared equals 1 over, we can substitute for what k was, 2n plus 1 squared times 1 minus 1 over 2n plus 1 squared equals 1 over 2n plus 1 squared minus 1. This is just algebra, which we can write as 1 over 2n times 2n plus 2 equals 1 over 4n times n plus 1. And we can split this as a partial fraction as 1 over 4n minus 1 over 4 times n plus 1. But we know all this was greater than bn minus bn plus 1. So we can observe from this that bn minus 1 over 4n is less than bn plus 1 minus 1 over 4 times n plus 1. This is just rearranging around that inequality. So if we consider the sequence bn minus 1 over 4n, you notice from this last implication that that sequence is increasing, right? Because this term is less than its just its successive term. So that means the first term, which is b1 minus 1 over 4 for n equals 1, is less than arbitrary bn minus 1 over 4n, which itself is this first inequality follows from the implication the sequence is increasing. And then the last one is just common sense because we're getting rid of the 1 minus 1 over 4n here. So bn minus 1 over 4n is less than bn, right? And then we can compute what b1 minus 1 over 4 is. We know a1 is e just by going back to the definition of an. Just a1 is e, and therefore b1 is just 1 because ln of e is 1, and then we get 1 minus 1/4 is 3/4. So we have a lower bound for bn. That's not sufficient. We need to find a lower bound for an. So just one more step is bn is ln of an. That's greater than 3 over 4. That implies that an is greater than e to the 3 by 4, because again, exponentials will respect that inequality. It's kind of easy to see. So we know an is bounded from below by a positive number. You can see e to the 3 by 4 is positive. Exponential of anything is positive. And an is decreasing and an is bounded below by a positive number. An must converge. An, the sequence we defined in the beginning, must converge. Fair enough. And this is the, the hence proved box that I have. Okay, that was lemma, that was proposition 1. Now it's time for lemma 1. This is a lemma is just an auxiliary theorem that we will need in the main theorem. And proving this is also easy. So the claim is limit as n goes to infinity of 4 to the n factorial squared divided by square root n times 2n factorial equals square root pi. Well, for this, the last video is extremely helpful, because if we notice the product we derived from the last video, the infinite sign representation, sine z equals z times product k equals 1 to infinity of 1 minus z squared over k squared pi squared. We plug in z equals pi over 2 and we just get the Wallace product, also known as 2 over pi equals product k equals 1 to infinity 4k squared minus 1 over 4k squared. We can flip this up doing it in invertendo on both sides. Pi over 2 equals k product from k equals 1 to infinity. We can write the 4k squared as 2k and 2k, and the 4k squared minus 1 as 2k minus 1 times 2k plus 1 in the denominator. Notice if we write some terms out, we notice that it's going 2, 4, and we're just squaring it. So the way the product is going is going 2, 4, 6, 8, and so on, and then we just double that because there's 2 pairs of 2's and 2 pairs of 4's. Similarly, in the denominator, there's no extra 1, but multiplying by a 1 won't affect it. So we have 2 pairs of odd integers at each time. We can write this as a double factorial. So in the numerator we have 2n double factorial, but there were 2 pairs, so squared, divided by, we could do a similar thing, but the problem with the odd ones is that we don't know if it's a plus 1, 2n plus 1 or 2n minus 1. So just let's just write them into 2 pairs. So 2n plus 1 double factorial times 2n minus 1 double factorial, which should just naturally follow from the form that we had here, splitting them into 2 pieces like that. So limit as n goes to infinity is 2n double factorial squared over 2n plus 1 times 2n minus 1 double factorial squared. This is just using the recursive definition of the double factorial. Now we can simplify this. We know that 2n double factorial is 2 to the n times n factorial, just pulling out the extra 2 factors, and 2n minus 1 double factorial is 2n the whole factorial divided by 2n double factorial. So we can write pi over 2 as limit as n goes to infinity of 2 to the 4n n factorial to the 4th power divided by 2n factorial squared times 2n plus 1. Now take the square root on both sides. Square root pi over 2 equals limit n goes to infinity 2 to the 2n n factorial squared divided by 2n factorial square root of 2n plus 1. Limit as n goes to infinity of 2 to the 2n is 4n n factorial squared, and we get an extra factor of square root 2 from that pi, divided by, because we're just multiplying by square root 2 on both sides, divided by 2n factorial square root 2n plus 1. Now we can just take the 2 and put it in the denominator square root like that, n plus 1 half in the denominator like that, and notice that as n goes to infinity, n plus 1 half is the same as n, because all that matters is the leading power in n. The coefficient of the leading power in n is all that matters. So we notice that limit as n goes to infinity of 4 to the n factorial squared over 2n factorial square root n, because we can replace this with an n as I said before, equals pi, square root pi. And that's all we had to show for this lemma. You may not see why this is useful right now, but it's going to take us exactly to where we want. And again, hence proved. Now, lemma theorem 3 is the main theorem, and theorem 3 is actually going to implement lemma 2 as promised. So let's define capital A to be the limit of the AN sequence. We know the AN sequence converges. Let's just call that limit A, and it's going to be some number, some positive number. So A, capital A, is limit as n goes to infinity of AN. And what's AN? It's limit n goes to infinity n factorial over square root n, n to the n, e to the minus n. And we want to show that that's equal to 2 pi. So the main idea is to show that the limit that AN converges to is square root 2 pi. Okay, so use the lemma we had before. We have square root pi equals limit n goes to infinity 4 to the n factorial squared over square root n to n factorial. Now we can multiply and divide by this weird looking factor in the numerator and denominator. So the factor we're multiplying and dividing by is square root n to the n e to the minus n whole squared in the numerator, while we also divide that inside the the square of the n factorial. We can write them together under the same power, divided by square root n. Everything else is the same in the denominator, except we're doing the same for the denominator. Instead of actually having n, we're having 2n. So it's the similar procedure. So square root 2n to the 2n e to the minus 2n is that factor. We don't have a square now, so we can just consider the 1 power of this. Square root 2n to the 2n e to the minus 2n. Now notice that this is actually just a, right? Because we can split this into a product of limits. We know that this thing in the bracket here that's being squared is an, and we know an converges, so we can write this as a product of limits. And when we operate the limit on this, it just gives us a but squared, a squared. The factor in front will just, we can just simplify that out. N times n to the 2n e to the minus 2n divided by square root n. Now doing a similar thing in the denominator. Now only thing is to notice that as n goes to infinity, n or 2n are all the same. So, even though it has a 2n, it's actually going to converge to the same value, capital A. Just because, limits as n goes to infinity, they don't matter if we have some constant multiplied with the n. We can just change the variables and we get the same limit. So A, capital A, square root 2 pi, and then we have 2n to the 2n e to the minus 2n. We can cancel so many things. A is just a number, so we can just always pull it out the limit. We have A times limit n goes to infinity of 1 over square root 2. All this was equal to square root pi, so we can just see by rearranging that A, capital A, is square root 2 pi. So we have basically proved that limit n goes to infinity n factorial over n square root n to the n e to the minus n, which was the sequence an, is equal to capital A, which is square root 2 pi. That means for large n, we can write n factorial can be approximated by, that's what this curvy sign is, square root 2 pi n, I'm just grouping terms, n over e whole thing to the n. And that is the famous Stirling's formula. So that means whenever you have the factorial of a really large number, like say 100 or 1000, because factorials grow really fast, you can just substitute, you can approximate that value, because the computation can get very tedious. You can approximate that value using the right hand side of this approximation, which is square root 2 pi n over e whole thing to the n. Now this Stirling's formula has many applications regarding the gamma function. One such application is improving the Gauss representation of the gamma function. Now I made a video back when I was immature, and the proof is not that rigorous in that video. But in this video, I'm actually going to try to be a little more professional with that. So let's start with what we have. So we have to show that limit n goes to infinity of n to the s n factorial over s times s plus 1 dot 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 s plus n. That is the Gauss representation of the gamma is equal to the gamma of x. How are we going to do that? Well, let's just work with it, and Stirling's formula is going to be the intermediate step here. So limit as n goes to infinity of n to the s n factorial over, we can write the denominator as gamma of s plus n plus 1 divided by gamma of s equals gamma of s times, now we can, it goes in the numerator, like gamma of s limit n goes to infinity n to the s n factorial over gamma of s plus n plus 1, which we can write the gamma of s plus n plus 1 as s n plus s whole factorial. The numerator is the same. Now once we see a factorial in the denominator, our eyes should light up with joy, because we have exactly the kind of treatment we need of the factorial as n is large, because of course we're taking the limit here, n is large. Stirling's formula can be applied in this case, and we can just substitute, use the Stirling's formula in the numerator and the denominator. So we get n to the s, and then in multiplied the entire thing in brackets with square root 2 pi n to the n plus 1 half e to the minus n divided by square root 2 pi n plus s raised to n plus s plus 1 half e to the minus n minus s. I'm just substituting for using the Stirling's formula that we have here for each of those numerator and denominator factorials. And in the end, we just get n to the n plus s plus 1 half e to the s divided by n plus s raised to n plus s plus 1 half. We can club all the denominator together. 1 plus s by n raised to n plus s plus 1 half. And n plus s plus 1 half in the limit as n goes to infinity is the same as n, or more precisely, if you multiply each of those powers separately, you notice that all of them disappear except when we have n in the power, and we notice that 1 over s over n, the whole thing to the n, is actually e to the s by the definition of the exponential. So that cancels off with the e to the s in the numerator, and we get gamma of s, which is exactly what we wanted to show. So we have gamma of s equal to limit n goes to infinity and n to the s n factorial over s times s plus 1 dot 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 s plus n, which is the Gauss representation of the gamma function. And this Gauss representation actually helped us, if you remember, to derive the Euler reflection formula of the gamma function, and also the digamma function, and the Mittag-Leffler expansion, and all those other nice things actually followed. Even the Weierstrass definition of the gamma function followed, which had the e to the minus Euler-Mascheroni constant times z in the as one of the terms. Anyways, I just wanted to make a video about the Stirling's formula for a long time, because we're gonna need it for something known as the Gauss multiplication formula of the gamma function, which I tried to do on my own. It was hard, but anyways, that's it for this video, guys. I hope I see you in the next video. Please like, share, and subscribe to my channel, and peace out.